Okay, I think we should be all set. So yeah, as Sean mentioned, today I will be talking about how we can thrive in an increasingly digital ecosystem. And we actually pushed this analogy quite far in comparing ecosystems to actually natural ecosystems. The view we are gonna, I will be presenting is from a knowledge engineering view. It's most of the presentation is based on a preprint we recently published on arXiv called Knowledge Engineering for Wind Energy. So you can, I'm going to provide links and you can look up for it later on. So without much further ado, let's go into dive into the presentation. And before going into the actual topic, I wanted to start probably with a question, which I'm sure many of you have been pondering over years. How do you compute the volume of a cow? And of course, that's a very important question. And the well-established answer to that is easy. You start with the assumption of a spherical cow in the space, in the vacuum of space. But on a serious note, this is what I want to talk about. The elephant in the room, in this cow, the cow in the room is what is knowledge engineering? And rather than talking about like what knowledge engineering is, I will probably actually would want to talk more about why knowledge engineering, or what kind of problems it addresses, right? So the answer to that, it has many layers, and we could go very deep into this over some like soft drink, maybe milk. But let's start from the surface. And on the surface, the answer is context, right? So for knowledge engineering, context is everything. So as humans, in our case, data scientists and wind energy domain experts approach their data, they will always find this data in some context. And otherwise, it's just numbers. In digital case, just ones and zeros, devoid of any meaning. It just might have been cows in a vacuum of space. So this brings us next to the next layer underneath the context, which is representation. How do we represent context, or more generally, how do we represent knowledge? And here the discussion can quickly go into philosophical turn, and we can start talking about things like abstractions and concepts, and all the way to Platonic ideas, and all discuss about Plato and what does it mean to exist, and what does it mean to be, and like the Belgian surrealist painter in his René Magritte in his painting, The Treachery of Images, said for it, oh, the famous pipe, how many times I've been reproached for it, but it is just a representation, is it not? If I would have written on my picture, this is a pipe, I would have been lying. So I wanted to talk about today about representations, about knowledge, but let's not go too much philosophical, and let's remain focused on wind energy. Here is another image that provides contextual information, right? For example, we can see that the wind turbines in the back are operating in the different conditions. They're in the wake of other wind turbines. So how do we describe what's happening in this picture? Or another question we would be interested is, given the sensor data we have available, what are the methods to model wakes, or how to do flow reconstruction in general? Yet another image of not a gearbox or a generator, it's just a representation of or like an image. And questions people might be answering like, oh, how do I actually represent information about this particular wind turbine? So I have a wind turbine, it has certain gearbox, certain generator, and we want to share it. And we want to share it so that we can answer questions like, giving the warnings, for example, of my monitoring systems, what parts should I order? Or when should I schedule a maintenance for the minimal downtime cost? And obviously, the problem of representation is not a new one, and we humans have dealt with it for many centuries. And the obvious question to representation is we need some kind of language. We usually deal it with English language, we all know it. But here we uncover another layer under context and under representation and under language, understanding and interpreting. So this is the maybe some people know this is a Rosetta Stone, and people would not be able to read it unless the information on it was not represented in 3 different languages. So going to modern times, the language is the digital language. It has to be machine understandable, and the representations we do have to be machine understandable. So no more carving on obelisks. We actually have, we interact very differently with information and with data in modern days, which brings us to the situation where we have right now, where we have different actors working with data. Sometimes it is one person, but in many cases, when the problems become complicated and the challenges grow, we start to see this diversification. We can have data scientists, data managers, data engineers, and knowledge engineers. So, and all of them are working to this common goal, which is developing some AI systems, which in theory have to facilitate the decision and then provide us with actual information. So, so while working towards this common goal of developing AI systems, how do knowledge engineers actually represent information? How do we develop and represent context, and how do we deal with metadata? Or answering in another way, following up to what we've been talking before, how would, for example, a knowledge engineer would represent a wind turbine? And again, the answer can merit a whole other talk. We'll go in the series of talks, and in the preprint we have published, we dedicate specifically the first part of a paper to overview of knowledge engineering and knowledge representation concepts and technologies. But to have it like a basic, like just a basic idea, and to understand a bit about what is coming up, the main idea to represent things is to develop things called ontologies. And ontologies is one of those things that it's quite difficult to explain in a few minutes what they are. Here is another representation in the slide of a wind turbine as a part of an ontology, that follows a schema.org ontology. And we can see that here, for example, we define concepts like a product and a product model and organizations, and we can define relationships between things. For example, that certain organization is the manufacturer of a product, and another organization can own a product, and the product can have a model. And all of this is actually, if we think about it, is the contextual information formalized or represented in the formal way that is later on can be machine understandable and human understandable. So knowledge engineers start dealing with quite complicated technology stack to represent these ontologies and to represent the data. In particular, when talking about metadata or about context, there is the idea of linked data. Many of people who deal with metadata on a general basis, they would know about linked data. And again, this gets very complicated very quickly. I don't want to discuss this whole technology stack, but the main idea is using this technology, it's possible to build the AI systems or the digital twins that I showed before in the center of a Venn diagram we've seen. So given this, what we did in the paper, we went ahead and we looked on how many of these technologies have been adopted in wind energy domain so far, and what is the state of the art, let's say. So we performed a search of all the existing ontologies. The common word, it's also called something that people call semantic artifacts. So basically these formal models, these representations of context that are formalized in a way using the technology, different technologies. And so in here, there would be all kinds of these semantic models, these models that represent context, ontologies, taxonomies, schemas. And what we found after looking is that majority of what has been developed so far covers mostly the wind farm operation phase of a life cycle. There are several ontologies or semantic artifacts that were dealing with wind farm planning, and then a couple that were cross-general across all the fields, and I think only actually very few that deal with wind turbine design. And this is also reflected in what were the audience or the target for this kind of developments, and most of them it was developed for energy producers and energy and the wind farm operators, and a lot of groups were excluded out of this existing semantic artifacts. So we saw that in terms of life cycle of wind energy assets, there are no semantic artifacts that cover end of life phase and project selling buying phases. And in terms of stakeholders, there were very few semantic, or actually there were none that were targeted, for example, for public or landowners or finance and insurance people. So looking even further into it, we saw that the adoption of these semantic artifacts was very low in the wind energy community, as in general, when compared to what's happening in other domains, and especially in domains that are much further advanced, like biomed and manufacturing. So, and the reason we could identify or target out of it is what we can see is majority of the semantic artifacts didn't actually adopt the linked data technologies. They were not published as linked data. So that technology stack I showed before, it didn't get all the way to adoption and development with it. So in this, so particular wind energy got stuck in this like negative feedback loop of the semantic artifacts not being published, not being maintained, and not being adopted. So obviously, when we were looking into the representations, we couldn't skip the kind of like an ultimate form of representation of thing, which is a digital twin. Some people will say the absolute, and ask me about the digital twins at your own risk. We can talk about it for very long. But again, based on our analysis, we performed the search on Scopus publications with the keys of wind energy, wind turbine, wind power plant, and digital twins and decision support systems. And again, here we saw that very few of the publications even mention semantic artifacts. I think only 35 out of 181 publications even have any mention of semantic artifacts, and even lesser actually had some concrete examples of these. So based on that, we developed several recommendations, and as I mentioned, we pushed the analogy with actual ecosystems quite far. So we organized our recommendations into 3 groups: organization and diversity, productivity, and resilience. So let's start with organization and diversity here. the first point I mentioned is a stakeholder analysis. So performing an analysis that is similar to the diagrams I showed before. The problem we found there is that there are not even taxonomies or even classifications of all existing actors and all existing activities in the wind energy sector as of right now. So even to perform a classification of what there is and what are the gaps, we are even lacking this base layer of understanding, well, what are the actors at play, what is at play here. The next point I mentioned is inclusive stakeholder engagement. So as I showed before, there's this disproportionate representation for energy operators for tasks like maintenance of wind turbine and much less towards the other groups and activities. This also includes the comprehensive digitalization of entire wind energy sector. So looking at all the stages of wind turbine assets, covering also things like end of life and dealing with data that comes from those areas. Another option I mentioned here is balancing aggressiveness with simplicity. To dive more deeper into it would require a bit more discussion on actually knowledge engineering concepts, but the idea is the complexity of models, of the representations we develop can be also balanced. There is not always the necessity to develop very complex models, very complex representations when we lack sometimes, and sometimes even simpler models will suffice, just simple classifications, simple taxonomies. Going to the next point, which is productivity. Here, I mentioned generations of new semantic artifacts and standards. So as you could have probably noticed in the slides, there were only 20 semantic artifacts that are wind energy specific. There were a few more that were cross-domain and or related to wind energy, for example, like material sciences, or the one that covered the areas of energy as more general, higher level representations. But to compare, for example, ontology hosting portals from Biomed has more than 1,000, I think, ontologies or semantic artifacts already published and hosted there. So the wind energy community right now really lacks these new representations, these new semantic models that are commonly accepted, and are used by people across the community. And this is partially right now being addressed within IEA Wind Task 43, then work group 2 that will be focusing on developing some of these new models. The next point I mentioned here is cross-pollination, so which consists of several topics, and in here one topic is alignment between different models within the domain itself, but also with alignment with the cross-domain and other domains that are related to wind energy. Because as of right now, the linked data and semantic web technology stack is not being adopted by wind energy community, it's very difficult to realize this alignment. And the second problem, as the ontologies that already exist, they are not published anywhere, the community is not adopting them and cannot align to them. So here the effort that we are doing and our group will be opening is we plan to have an ontology catalog developed called the Techno Portal, which basically will host all of the ontologies I mentioned before, and which will make them available as linked data. The other point I mentioned here is information access and transparent decision making. this has to do also in part with engaging the wider community, engaging public, engaging all the actors in the field so that they have access to all the contextual information. The activities here can be development of knowledge bases or expert system, development of transparent, these knowledge bases can have a front-facing API as like some kind of website that can provide actually people with information. Obviously, all of this is tied up with the topic of automation and workflow development, which the semantic technology web stack is actually enabling. So, and last but not least, the point is the resilience. So, as I mentioned before, most of the semantic artifacts that already exist in wind energy community are not maintained, and therefore they also have very low adoption and not being reused right now. So here I talk about FAIR principles, which stand for findable, accessible, interoperable, and reusable. I think many people might be familiar with those. So the development of new standards should follow those FAIR principles. And another point, the maintenance here, I think the wind energy community can benefit a lot from the open source software community and their practices. So using resources like GitHub and other platforms that enable this maintenance in a sustainable manner. So to close up, I would want to outline a little bit what is the future outlook and research activities here. As I already mentioned, the IEA Wind Task 43 is going to be working on, has several groups, and one of which will be dealing with developing of new ontologies or new representations. And then the other activity is a techno portal, which is an ontology hosting portal using a semantic web technology stack. And then between other things that are just more of like an interest and the topics we can talk about is large language models and formal rule-based systems, hybrids or fusion, which is a very hot topic right now due to the success of large language models like ChatGPT, and everyone wants to talk about them. But the problem and addressing the problem of, I don't know if maybe some people are familiar with, of large language models hallucinating data or not providing data that is verifiable, can be solved in part by combining this with formal or rule-based systems in where the knowledge produced can be actually like explicitly proven. Another area in this research is the relational machine learning, and all of these two topics in theory should enable like automated knowledge extraction. Another interesting topic is the development of recommender systems based on the technology stack. So after the base layer of actually the semantic artifacts, these ontologies have been formed and can be used, based on top of that, it's possible to start developing recommender system, much more smart AI systems. It's another area of interest would be workflow creation and optimization. And here we can talk about things like applied category theory or Markov decision process trees. So all of the things that can come up after the data is structured and presented. So at this, I think I can conclude. Finishing up with a picture of Plato and the Platonic ideas. So this is Plato as LLM transformer generated by another transformer, which is a DALI. So thank you all for listening, and I'm very keen to hear your questions.
Great, thank you so much. I think now we can open up for questions from all on the call.